Welcome back, Kappa, to Remote Learning Week 6. Today we're going to talk about potential energy diagrams. And before we get started, we're going to do our mindful minute. So find a comfy seat, sitting with a mindful body. And I encourage you guys to close your eyes, or you can look at the animation on the screen. We'll take deep breaths together for 1 minute. Inhaling through the nose, nice deep breath. And exhaling. Inhale, fill your lungs. And exhale. Nice deep breath in. And full exhale out. We're halfway there. Inhale through your nose. And exhale. Inhale. And exhale. Last one. Nice deep breath in. Full exhale out. Allow your breathing to return to normal. And when you're ready, you can slowly open your eyes. Okay, so today we're talking about potential energy diagrams. Before we do that, I'm going to review some questions from last week. So these were some questions that were commonly missed. And, oops. So I'm going to go over these. Okay. If the concentration of A is decreased, where is the stress on the system? Which direction would the equilibrium shift? So we talked about equilibrium and the different ways equilibrium can move in a reversible reaction. So for this one, if A is decreased, where is the shift? The shift is on the left, meaning there's not enough reactant in the reverse reaction. So equilibrium will shift to the left to create more reactants. Okay, next one is really similar. If the concentration of C is decreased, where is the stress on the system? Which direction would the equilibrium shift? So if there is a a decrease in C, that means the stress is on the product side and that there is not enough product. So the system will shift to the right to create more product. These two questions were commonly missed. So you just want to look at basically like which side has too little or too much and how does it balance out. Okay, here is a do now question about equilibrium. Given the diagram representing a closed system at constant temperature, so we see a stoppered flask, that just means it has a stopper in it. Which statement describes this system at equilibrium? So we see H2O gas, water vapor in the beaker, and H2O liquid, water, in the beaker as well. So at equilibrium, the mass of H2O liquid equals the mass of H2O gas. The volume of H2O liquid equals the volume of H2O gas. The number of moles of H2O liquid equals the number of moles of H2O gas, or the rate of evaporation of H2O liquid equals the rate of condensation of H2O gas. We know that with equilibrium, what's equal is the rate of the forward and reverse reaction. And furthermore, the concentrations would be constant, meaning they don't change because the rates of evaporation and condensation are equal. So, the one question on your form last week was if you could have a mole of anything, what would it be? Remember, mole is a unit of measurement to measure really, really, really tiny things like atoms and molecules. And the most common answer that you guys said was you would want to have a mole of money, of course. The answer that I like the most, that I resonate with the most, was a mole of French fries. And the most creative answer was a mole of wigs. So by the way, I Googled wig and Rihanna was like one of the first ones on the page. I don't know why, but I guess because her wig is pretty nice. So thank you for your creativity. Also, how amazing do these French fries look? All right, today's learning target is I can diagram the energy of a reaction. So pause the video now so you can write down today's learning target. Okay, so with last week, we talked about collision theory. And if you recall, this is when atoms or molecules collide and create a reaction. So basically, whenever this is happening, whenever a chemical change is occurring, let's review actually. How do we know this is a chemical change? That's because new products are being formed and atoms are being rearranged. So, whenever there's a chemical change, there's also a change in energy. So, that's what we're going to look at today, the change of energy during a chemical reaction. So, we're going to start with a video from TED Ed called What Triggers a Chemical Reaction? And there are some check for understanding questions with this in your Google form.
You know how sometimes you go to bake a cake, but your bananas have all gone rotten, your utensils have rusted, you trip and pour all of your baking soda into the vinegar jug, and then your oven explodes? My friend, you and your chemical reactions have fallen victim to enthalpy and entropy, and boy, are they forces to be reckoned with. Now your reactants are all products. So, what are these E words, and what's their big idea? Let's start with enthalpy, an increase or decrease of energy during a chemical reaction. Every molecule has a certain amount of chemical potential energy stored within the bonds between its atoms. Chemicals with more energy are less stable and thus more likely to react. Let's visualize the energy flow in a reaction, the combustion of hydrogen and oxygen, by playing a round of crazy golf. Our goal is to get a ball, the reactant, up a small rise and down the other, much steeper slope. Where the hill goes up, we need to add energy to the ball, and where it goes down, the ball releases energy into its surroundings. The hole represents the product, or result of the reaction. When the reaction period ends, the ball is inside the hole, and we have our product, water. This, like when our oven exploded, is an exothermic reaction, meaning that the chemical's final energy is less than its starting energy, and the difference has been added to the surrounding environment as light and heat. We can also play out the opposite type of reaction, an endothermic reaction, where the final energy is greater than the starting energy. That's what we were trying to achieve by baking our cake. The added heat from the oven would change the chemical structure of the proteins in the eggs and various compounds in the butter. So that's enthalpy. As you might suspect, exothermic reactions are more likely to happen than endothermic ones because they require less energy to occur. But there's another independent factor that can make reactions happen: entropy. Entropy measures a chemical's randomness. Here's an enormous pyramid of golf balls. Its ordered structure means it has low entropy. However, when it collapses, we have chaos everywhere, balls bouncing high and wide, so much so that some even go over the hill. This shift to instability, or higher entropy, can allow reactions to happen. As with the golf balls, in actual chemicals, this transition from structure to disorder gets some reactants past the hump and lets them start a reaction. You can see both enthalpy and entropy at play when you go to light a campfire to cook dinner. Your match adds enough energy to activate the exothermic reaction of combustion, converting the high energy combustible material in the wood to lower energy carbon dioxide and water. Entropy also increases and helps the reaction along because the neat, organized log of wood is now converted into randomly moving water vapor and carbon dioxide. The energy shed by this exothermic reaction powers the endothermic reaction of cooking your dinner. Bon appetit!
All right, so you can pause the video now and try the check for understanding questions, or you can do them at the end of the lesson. So, two concepts that were covered in the video under enthalpy were endothermic and exothermic reactions. So, enthalpy is the change in energy during a chemical reaction, and there are two types of changes. The first one is endothermic, where energy is absorbed and stored as potential energy in the bonds of a chemical. And the physical result is this endothermic reaction feels cold. And we can remember that energy is being absorbed because the prefix endo means in. So energy is going in. And there is a quick picture I want to show you guys. We'll just look at the left right now. This is an endothermic reaction when ice melts. So the reaction is absorbing heat, which is a form of energy, causing the phase change. Now, this actually is not a chemical reaction because remember, water solid going to water liquid is a phase change, which is not a chemical reaction, but this does show a change in energy. That's why this example is used. So, heat going in and warming up the ice is endothermic. The other type is an exothermic reaction. So exo means out. So energy is being released. As thermal energy, it can also be, excuse me, I don't know why that's happening. It can also be released as light. So energy is released as heat and light, and the result is the reaction feels warm. So it's giving off heat and light. So if we look at the right side of this picture, an exothermic reaction is when anything is burned. That is an exothermic reaction happening. Also, some chemicals, when you mix them together, they actually do get hot to the touch. And some chemicals, when you mix them together, they feel cold to the touch. So pause the video now so you can write down these two reactions. Okay, so the different components of energy change in a chemical reaction are 1, energy of the products, 2, energy of the reactants, 3, the energy to get the reaction going, and 4, the total overall energy change. And we show these 4 things through what we call a potential energy diagram. So that looks like this. Now, in your notes, write down this graph. It doesn't have to be perfect. We're going to go through and label the different parts of this graph. So on the y-axis, we have potential energy being measured, and that is increasing as it goes up. And then on the x-axis, we have the progress of the reaction, which is also sometimes called reaction coordinate, but you can just think of this as time, basically. So over time, increasing to the right. Okay, now here's our graph. It looks really weird. I've never seen a graph like this before in math. So this actually represents different parts of the reaction. So the first one is energy of the reactants. Oh my gosh, why does that keep happening? My bad, you guys. Cancel. Okay. Energy of the reactants is the very first line. Now, this makes sense because the reactants are what you have in the equation first. So this flat line here represents the energy of the reactants. Now, can you guess where is the energy of the products? Your energy of the products is going to be down here. So the end of the reaction, right? Because this is later in time. Now, the next thing would be this little hump. So what do you think this would represent? This represents the energy that it takes for the reaction to get started. So to go from reactants to products, there is this little hump, and we call this the activation energy. So the energy needed to start the reaction. If you think back to the video, it was represented by a hill when the little guy was playing golf. So in order for the golf ball to go down the hill, it needs to actually increase in energy before it can go down the hill. So in chemical reactions, reactants need to gain energy and go over this activation energy hump before the reaction can actually be completed. And the reverse would be true. The energy of the products would need to increase, go through the activation energy to turn back into reactants. So think about like when you're walking up a hill, it takes energy for you to get to where you're going. That's all it is. And you're going to want to write down this definition as you annotate it on your graph. Okay, so pause the video if you need to. And the next part of the reaction is this area underneath the activation energy. So we can actually take our pen and we can dissect this graph into different parts. And I encourage you to do this on your notes. All right. So the first line here gives us our energy of the reactants and the activation energy. And this area down here is actually the energy of the reactants minus the energy of the products. So it's actually this whole energy value minus this value gives us this value, which we call the heat of reaction. So this is the difference in potential energy of reactants and products, which is why I said you can subtract these two, and it gives us the overall net energy change. So the actual energy change in the chemical reaction, because these kind of cancel each other out. For this gets canceled out, right? So if you subtract that, you're just left with this. That's the overall net energy change. And it's represented by delta H. Do you guys remember what delta means? Delta means change. And H is the unit for enthalpy in this case. Okay, so annotate this in your notes. Pause the video if you need to. Okay, which diagram represents an endothermic reaction and which represents an exothermic reaction, and why? So take a look at the two graphs and notice what is different between the two. I'll just draw a line here to separate them. So graph A and graph B, what's different between them? Well, we see that reactants and products are at different energy levels. So if we think of an endothermic reaction, endo means in, so energy is going in or being absorbed. Which graph shows energy going in or being absorbed? Graph A, because products are at a higher energy level than the reactants, than where it started. So energy is going into this reaction, so this is our endothermic reaction. And if we remember, exo means out. Energy must be going out of this reaction. So graph B shows this because products are at a much lower energy level than the starting reactants. So energy is leaving this reaction or being given off. So this is our exothermic reaction. Now for your assignment this week, you're going to use these graphs, and there are questions that will give you a type of reaction, and you have to determine, is it endothermic or exothermic, and which graph represents that. So some of the reactions are written out as sentences, and some of them are written out like chemical formulas. Okay, so remember this graph for your assignment. And this week there's one lesson and one assignment because this lesson is pretty long. Okay, is this an endothermic or exothermic reaction, and how do you know? Well, we see over here 58 kilojoules. If you remember from unit 1, joules is a unit of measurement for energy. So energy in this example is where? It's a product. So is this endothermic or exothermic? This would be exothermic because energy as a product means it's being given off. So whenever energy is being given off, or heat is being given off. This is an exothermic reaction. So energy is released as a product and it's written on the product side of the equation. If this helps you to write it down, pause the video now. And for your graph, products are lower than where the reactants started. And for endothermic, heat is written as a a reactant. So that's an endothermic reaction. So whenever heat is absorbed as a reactant, it's going to be on the left side of your equation. It's an endothermic reaction. And your graph that represents that is when your products end at a higher energy level than where your reactants started. You can pause the video now if you want to write this down. All right. Here is a practice question. It says a 1 mole sample of glucose completely reacts with oxygen as represented by the balanced equation below. So here's glucose solid plus oxygen gas gives us carbon dioxide gas and H2O liquid plus energy. Do you guys know what reaction this is? You've definitely learned it before. This is the reaction for cellular respiration, where your body takes oxygen, right? When you take a nice deep breath, and then it reacts with the glucose to create energy and the byproduct, carbon dioxide, which is what you exhale. Throwing it back to the living environment. All right, so this question's asking, using the axes in your answer booklet, that's the axes right here, complete the potential energy curve for the reaction of glucose with oxygen. So basically, you're going to draw a graph. You're going to draw a hump, but we don't know what it looks like. So we have to look at our reaction. What do you notice about this? Will it be endothermic or exothermic? We see energy over here, again on the product side. So that means this is going to be an exothermic reaction. Whenever we have an exothermic reaction, the graph looks like the energy of the products being less than the energy of the reactants. So this first line here is actually a clue. This is the energy of the reactants. I know energy of the products needs to be lesser or lower. So it should be like down here somewhere. And then all I need to do is draw a hump like this. And that's the energy of my reaction. Now, why did I draw it like this? Because remember, the first part here is our activation energy, the energy to get the reaction started. And then that other part, just imagine that straight. The other part would be our energy of the reaction. So that difference between energy of reactants and products would be our delta H here. And then up here is our activation energy, which is abbreviated EA, like energy activation. Okay. So there is something that can change the energy of a reaction, and that's called a catalyst. So again, throwing it back to living environment, what does a catalyst do? Catalyst speeds up chemical reactions. So that would have an effect on the energy of the reaction. Here is a really exaggerated example of what a catalyst can do. You might have seen a video like this before.
9:46 on this Saturday morning. Time to have a little bit of fun. Carl Nelson is here from the Imagination Station, and you brought some funky new glasses. Thank you. I'll put these on. Looking styling. What are we doing today?
I brought with me hydrogen peroxide.
Okay.
You probably have this in the medicine cabinet at home, right?
Absolutely.
What do
Yep.
you do with it?
Put it into cut.
Yeah.
Clean things off, right?
Doesn't really work that effectively for killing bacteria and cleaning out cuts.
Oh.
Actually, check out our
Right.
Facebook page. I put a posting up there about how it doesn't work that well.
Yeah.
But one of the things it does do, here, I have a hunk of raw liver. If you could
Oh,
just
good.
go ahead and hold that.
Thanks, Carl.
Your body as a part, I know, isn't that cool?
Yeah.
Your body as a part of metabolism actually generates hydrogen peroxide in its cells.
Okay.
And it's very strong oxidizer. You want to get rid of that hydrogen peroxide. There's something called catalase. It's an enzyme in your body
Mhm.
that will break down the hydrogen peroxide into water and oxygen gas. So beef liver actually has catalase in it. And when you squirt the hydrogen peroxide on, just like on a cut,
Mhm.
I assumed you didn't want us to like cut you or anything to show how this works, right? It generates oxygen gas. Okay. And it looks really impressive, like it's doing something. But again, it's kind of a myth that it actually kills any sort of bacteria or cleans the wound out.
Oh, good to know.
But you can do something really cool with this. You can drop the liver now.
Okay.
We're done with that.
Okay.
So what I brought with me is 35% hydrogen peroxide. This is 10 times stronger than what you have at home, hence the gloves and the glasses. You don't want to get this on your skin.
Okay.
And it gives off oxygen gas if you give it a catalyst, like catalase,
Mhm.
or I brought a different catalyst with me. Now, it's really cool because it can generate enormous amounts of oxygen gas. So we're going to trap that oxygen gas in some soap, okay?
Okay.
Do a nice little squirt of soap in yours. I'll do one in mine. And what we're going to do is simply pour a catalyst into this container of hydrogen peroxide. We'll break down the hydrogen peroxide into water and oxygen gas. Now, since we have soap inside here, we're hoping for something
Is this going to explode?
kind of
Okay.
dramatic. Yeah,
Uh-huh.
I don't know. And you know what? Go ahead and hold this.
Do I need to step back here?
No,
Carl?
stay right where you are. But let me do mine first.
Okay.
Let's do a little test here. See what mine looks like, and then you can try yours. So that's the technique. Just dump it right in and see what happens.
Oh, wow. Okay.
So
Whoa.
we're releasing
Okay.
lots and lots of oxygen gas. Okay. So why don't you go ahead and do yours now? Yours is a little bit different container. It's got just dump it in really quick.
Okay.
Perfect. Yours is like more of a and you just generate tons and tons of oxygen. It's being trapped by the soap.
Wow.
Okay. It's like a
Okay.
supersized version of what kind of happens when you pour it on your body,
Sure.
where that catalase enzyme breaks it down.
But again, we're not actually cleaning anything,
Well,
if you will.
Technically, the hydrogen peroxide, when it generates this oxygen, can kind of dislodge big hunks of stuff that
Okay.
might be in a wound.
Mhm.
But in terms of killing the bacteria, it's not really all that effective.
Sure.
What
Okay.
it is, if you stick your hand over that, you can feel it's giving off some
Oh,
decent
some heat. Yeah.
It's an exothermic reaction, so it gives off a lot of heat when it breaks down, and it's just really cool.
So where would you see something like this?
Okay, we're going to stop there. So that was a catalyst in action on a really exaggerated scale. So, what does a catalyst do? A catalyst speeds up a chemical reaction by lowering activation energy. So, it actually makes that hump on our energy graph smaller. So, this speeds up the forward and reverse reactions equally if it's a closed system at equilibrium, and it does not change or shift the equilibrium. So pause the video now so you can write this down. All right, a check for understanding. Given the reaction at equilibrium, A plus B equals C plus D, the addition of a catalyst will 1. Shift the equilibrium to the right, 2. Shift the equilibrium to the left, 3. Increase the rate of forward and reverse reaction equally, or 4. Have no effect on the forward or reverse reactions. So key word in this is the system is at equilibrium. And when the system is at equilibrium, the equilibrium won't shift because of a catalyst. So we know it's not 1 and it's not 2. What happens is the rates are increased equally. So both the forward and reverse reactions are increased equally. Now you might think, well, in the video, we saw that there was way more product formed, right? All of that oxygen gas, which was trapped in the soap. Well, that system was not at equilibrium because it was not a closed system. So that's why the there was more of the product formed in that example. Okay, so I want to take us back to this question. Now, here's our graph for the energy of the reaction for cellular respiration. Now, I want you to predict, what would the new reaction graph look like if a catalyst was used? So, how would the graph look different if the catalyst was used? Well, we know that catalysts lower activation energy, so actually, this hump would just be smaller. So it would take less energy for this reaction to get started, but everything else would be the same. So our activation energy just gets a little smaller in order for the reaction to happen faster, or with less energy, I should say. So it's like giving the reaction a different pathway to follow. And imagine thinking back to our TED video, if you're playing golf, it's going to be easier to play this game of golf on this hill because it's a smaller hill. Or if you're walking up a hill, it's going to be easier. It's going to take you less energy to walk up this hill. Okay, here are just two more graphs I want to show you with the potential energy diagrams with a catalyst. So notice the difference between the reaction without a catalyst, the red line, and with a catalyst, the green line. And here's another one. So again, just that activation energy is being lowered. There's a new pathway for the reaction with a catalyst. Okay, we'll do a check for understanding question. A catalyst increases the rate of a chemical reaction by 1, providing an alternate reaction pathway, 2, providing the required heat of reaction, 3, increasing the potential energy of the products, or 4, increasing the activation energy of the reaction. We know it's definitely not 4. We know that it doesn't increase the energy of the products, but what it does do is lower the activation energy, thus giving our reaction a different or alternate reaction pathway. Okay, and last one. Given the equation representing a system at equilibrium, which change causes the equilibrium to shift? 1, increasing pressure, 2, increasing temperature, 3, adding a noble gas, or 4, adding a catalyst. So I think we can agree it's not 3. It's probably also not increasing pressure. We haven't really discussed that. If you think it's adding a catalyst, that's actually wrong because this equation is at equilibrium. Remember that equilibrium will not shift due to a catalyst. But what would shift this would be increasing temperature. So if we increase energy, there would be a stress on the system, and the system would shift which way? It would shift to the right. Okay, so catalysts do not shift equilibrium if the system is at equilibrium. All right, so for this week, again, you have some check for understandings of this lesson, and then you have an assignment for the later part of the week. Okay? If you guys have any questions, feel free to email me. You're all doing great. Keep up the awesome work. And I will see you guys next week.